Alright, our third example is problem 38 from section 5.7. This problem gives us the 3x3 matrix 5, 20, 30, 0, 10, 20, 0, 0, 5. And it wants us to find the matrix exponential e to the at using theorem 3, which is using methods similar to what we used in our first example, which would be eigenvalues and eigenvectors. So what we're going to start off by doing is a minus lambda I to find our characteristic equation, which is minus lambda cubed plus 20 lambda squared minus 125 lambda plus 250. And from this we get that our eigenvalues are lambda equals 10 and lambda equals 5, which has a multiplicity of 2. In the essence of time, I'm going to skip over working out the eigenvectors for lambda equals 10 and lambda equals 5. For lambda equals 10, our fundamental matrix entry is x1 of t equals e to the 10t times 4, 1, 0. And for lambda equals 5, our entry is x2 of t equals e to the 5t, 4, 0, 0. Since lambda equals 5 has a multiplicity of 2, we are going to use this equation, a minus 5i squared. So we are basically going to multiply our initial matrix A by itself, which gives us the new matrix 0, 100, 400, 0, 25, 100, 0, 0, 0. From this, we were able to get the system 100y plus 400z equals 0, and 25y plus 100z equals 0. We then find that x is equal to 1, y is equal to 4, and z is equal to minus 1. So our eigenvector is v equals 1, 4, minus 1. Now to find our entry for our fundamental matrix, we are going to use the equation from the previous slide, which is x of t is equal to e to the lambda t times the eigenvector u plus a minus lambda I, u times t, plus a minus lambda I squared, u times t squared over 2 factorial, all the way up to a minus lambda I, r minus 1, times u, times t to the n minus 1, over r minus 1 factorial. So our third entry, x3 of t, looks like this. E to the lambda t is equal to our eigenvector that we just found plus a minus lambda I times our eigenvector times t, which looks like this. E to the 5t times our eigenvector 1, 4, minus 1 plus our original matrix 0, 20, 30, 0, 5, 20, 0, 0, 0, minus our eigenvector 1, 4, 1 times t. The reason there is no negative sign here is because I changed the addition sign to a minus sign right here. Then once we simplify this, we get that x3 of t equals e to the 5t plus 50 t e to the 5t, 4 e to the 5t, and minus e to the 5t. So now we can write our fundamental matrix, which is 4e to the 10t, 4e to the 5t e to the 5t plus 50t e to the t, e to the 10t, 0, 4e to the 5t, 0, 0, minus e to the 5t. And then we want to evaluate this at 0, which ends up being 4, 4, 1, 1, 0, 4, 0, 0, minus 1. We then also need the inverse of this matrix. I'm going to skip through going through the method of minors and cofactors just in the essence of time. But using that method, we get that the inverse matrix is 0, 1, 4, 1/4, minus 1, minus 15 over 4, 0, 0, minus 1. And we can now write that e to the at is equal to the fundamental matrix times the inverse matrix. So our final solution is e to the at equals e to the 5t, 4e to the 10t minus 4e to the 5t, 16e to the 10t minus 16e to the 5t minus 50e to the 5t times t, 0, that should be over there, 0, e to the 10t, 4e to the 10t minus 4e to the 5t, 0, 0, e to the 5t. And that's our final solution.